You know that moment on a roller coaster when you're going over the top of a hill and right before you throw up, you feel like you're hovering above your seat for a second? What would it feel like if that moment could last just a little bit longer? Probably something like this. Who does that? It looks so awesome!
My name's Emily Calandrelli, and I'm a host and co-producer of Exploration Outer Space on Fox.
Besides being a super awesome, intelligent woman, Emily has gotten the chance to go up in a plane simulating weightlessness
Twice.
No one's that lucky. These planes fly and dive in such a way that you feel like there's almost no gravity acting on you. It feels like you're floating in space.
Some people ask me if I've literally been to space.
See? Pretty funny. But maybe it's not actually that far off. If you consider the fundamental physics behind these two phenomena, it's a reasonable question.
But then I explain, like, no, obviously I did not, because going to space is really hard and dangerous, and I'm not even sure that I would be able to go to space.
Okay, besides the impracticality of getting to space, you know, like needing a rocket launch and years of vetting and training and all, you can't really tell the difference between diving in the zero-G plane, or the vomit comet, and actually being out in space. Well, I guess you could just look out the window.
The nose of the plane is pointing downward at about 45 degrees. So you can actually tell that you're diving toward the ground when you look out the window.
So there's that. But here's how. When you throw a ball up in the air with some sideways motion, it falls back down in this shape. You've probably heard it called a parabola. The pull of gravity makes the ball go faster and faster. It makes the ball accelerate. Now, if I threw you up with the ball, ignoring air resistance, you would fall in the same path, despite your difference in mass. So to you, it would look like the ball were just floating next to you. That's the idea behind the vomit comet. The zero-G plane flies in the path that an object in free fall would follow. It's the same parabola. So now replace that ball with a plane and you're both moving together. That is the path the plane follows during your segments of weightlessness, and that's what makes you feel like you're floating. But it still seems strange to me that you're falling, though you feel like you're floating. How can that be?
What you feel when you're in the aircraft is simply weightless. You are floating in the aircraft. And so to you, you feel like you're in space.
Can you explain to someone who's never felt like they're in space? Because you're like, you feel like you're in space, but
yeah,
you know,
like all those times you've been in space. It
yeah,
feels like
all
that.
those times I've been in space.
Another like analogy is when you're underwater and you feel buoyant. That's a little bit of a similar feeling. You're not going up, you're not going down, you really have nothing pushing against you.
Pause. This is a really important point. Much of the sensation of floating comes from not having a localized force acting on you. Think about when you're sitting or you're standing. When you're sitting down, you feel the pressure of the chair on just your butt. When you're floating, nothing needs to hold you up like that, so there's no localized pressure. You know those memory foam mattresses? They say you feel like you're floating on a cloud? That's because they're actually spreading the force out all over your body to make you feel more like you're floating. So even though you're falling in a plane,
if you don't look outside, you don't know that you're diving towards the ground. You don't feel that. What you feel when you're in the aircraft is simply weightless.
Now, how is this different from skydiving? Well, that's where air resistance comes in. When you jump out of a plane, initially you're falling pretty close to the rate of free fall. But at some point, you reach terminal velocity. This is where a lot of us get confused, because you're still falling, but you're not free falling anymore. The force of air resistance balances the force of gravity. So you don't stop, but you keep going at the same speed. And if you've ever skydived, you can definitely feel that force of air resistance on you. Now, as awesome as the vomit comet is, the feeling eventually takes its toll.
The most common question is, did I get sick? Because it's nicknamed the vomit comet for a reason. And it always sucks to answer that question because I want to be like, no, I did not. But I did.
The vomit comet does those parabolas over and over. You eventually get 30 of them. I imagine at some point you probably just want to get off that ride. But it still looks like so much fun. If you want to know more about the vomit comet experience, keep watching for more stories from Emily. Thank you so much to Emily for joining me at MIT. And check out her new show, Exploration Outer Space, on Fox in the fall. This is one of the first science shows hosted by a woman. Pretty awesome. Thanks for watching.
Hope you have a good picture there. Well, in my left hand I have a feather, and in my right hand a hammer, and well, I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects and gravity fields. And we thought where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon, and I'll drop the two of them here, and You know, hopefully they'll hit the ground at the same time. How about that? And that proves that Mr. Galileo was correct in his findings.
Superb, Dave.
Well, I always say there's nothing like a little science on the moon.
Now I want you to make a prediction. In my left hand, I have a standard-sized basketball, and in my right hand, a 5-kilogram medicine ball. If I drop them both at exactly the same time, which one will hit the ground first?
Ah, this is a trick one, isn't it?
The heavy will go down first.
Well, yeah, it'll drop faster.
They'll both hit the ground at the same time.
Give me a prediction.
I actually would have thought this one would go faster because it's heavier. Maybe it's that one.
Maybe this one, yeah.
So you reckon this will be
I reckon
faster?
that one will be faster.
So why does that make it go faster?
Because the weight pulls it down quicker.
What are we measuring when we say, oh, it's heavier? What are we feeling?
Gravity?
Go ahead. Yeah, that's... Oh.
Objects being pulled to the earth, I guess.
Okay, so which of these objects is being more pulled to the earth?
This one.
That one, the black one.
All right. Well, here's what we're going to do. I want you to hold both of those above your head. Don't worry. Can you get them really high? Can you? Okay, on the count of 3. Ready? 3, 2, 1.
Yeah! Exactly the same.
They fell at the same time. Exactly the same time.
They hit at the same time.
Was that what you expected to see?
No.
So what do you make of that?
I need to go read more books.
Magic?
Gravity is going to pull at the same rate, no matter how heavy or how light it is.
There must be some force that's dragging them down, and actually the actual weight of it doesn't matter.
Consider the acceleration of a bungee jumper. When does he experience the greatest acceleration? Is it A, immediately after leaping off the platform? B, when the rope becomes taut? C, at his fastest point? D, at the very bottom of the jump? Or E, on the rebound? Make your selection now. As a reminder, A is just after he leaves the platform, B, when the rope becomes taut, C, at his fastest point, D, at the very bottom of the jump, or E, on the rebound. Congratulations! You chose the correct answer, D. The bungee jumper experiences maximum acceleration at the very bottom of the jump. This is a counterintuitive idea for most people because they confuse the concepts of velocity and acceleration. At the bottom of the jump, the velocity is virtually zero, but acceleration is not. So what is acceleration? It is the rate at which velocity changes over time. It is very difficult for us to spot just by looking at it because our eyes track motion smoothly. So you have to think about the velocity at 2 different times. Right before the jumper reached his lowest point, he was going down, but after he reached it, he was going up. So while he was right at the bottom, his velocity was changing rapidly. In other words, while velocity was minimal, it was changing at the greatest rate. The key is to keep the two ideas separate, velocity and the rate at which it changes.